Now we move on to design of rigid pavement. Typically, rigid highway pavement are constructed of Portland cement concrete, and it may not have a base course between the subgrade and the concrete surface. So when a base course is used in rigid pavement construction, it is usually referred to as sub-base course. It is common, however, for only the concrete surface to be referred to as a rigid pavement even where there is a base course. So rigid pavement actually and concrete pavement are same, they have the same, they are synonymous, meaning to say they're the same, they have the same meaning. So of course, rigid pavement is, as mentioned, it is constructed with a Portland cement and concrete slab resting on a prepared subbase or granular material or directly on a granular subgrade. So the load is transmitted through the slab to the underlying subgrade by flexure of the slab. The flexible pavements are constructed of several thickness. So the rigid pavement actually have some flexural strength that permits them to sustain a beam-like action across minor irregularities in the underlying material. Thus, the minor irregularities may not be reflected in the concrete pavement. So, properly designed and constructed rigid pavements have long service lives and usually less expensive to maintain than the flexible pavement. So the maintenance for the rigid pavement is less compared to the maintenance of the flexible pavement. So the thickness of a highway pavement are normally ranges from 6 to 3 inches. So different types of pavement are constructed to carry heavy traffic load, although they have been used for residential and local roads. So what are the materials used for roadway pavement? So basically, one is the Portland cement. In most highway agencies use the American Society for Testing. We have the ASTM, which is the American State Highway and Transportation Officials, and specifies the designated for specifying Portland cement quality requirement. So based on the AASH2, we have different types of Portland cement. So we have the type 1, which is suited for general concrete construction. So there is no special properties that is required. So a manufacturer can supply this type of cement with no specific type is requested. Then we have the type 2, suited for a general concrete construction where the concrete will be exposed to moderate action of sulfate or where moderate heat of hydration is required. Then we have type 3. This is suitable for concrete construction that requires a high concrete strength in relatively short time. It is also sometimes referred as high early strength cement. Then we have type 1A, type 2A, and type 3A are similar to type 1, 2, and 3 respectively, but obtain a small amount of 4 to 8% of the total mix of entrapped air. Then we have the type 4, which is suitable for projects where heat of low hydration is necessary, while type 5 is used in concrete construction projects where the concrete will be exposed to high sulfate action. So we have here a table showing to us the proportion of the different chemical constituents for each of the type or the 5 types of cement. So we have here the cement type with their corresponding type. It's either 1 and 1A, 2 and 2A, 3 and 3A, 4 and 5. Then we have the next material for rigid pavement. We have the coarse aggregates. So the coarse aggregates as used in Portland cement concrete are inert material that do not react with cement and usually are comprised of crushed gravel, stone, and blast furnace slag. So this coarse aggregate can be one of the 3 materials or else a combination of 2 or all 3. So the major requirement for this coarse aggregate used in Portland cement concrete is the gradation of the material. So the material is well graded with a maximum size as specified. So the material retained in the number 4 sheave is considered a coarse aggregate. Then we have here our next one. We have the fine aggregate. So sand is mainly used as the fine aggregate in Portland cement concrete. Specifications for this material usually include grading requirements, soundness, and cleanliness. So the standard specification for the fine aggregates for Portland cement concrete, or the AASHTO designation M6, give grading requirements normally adopted by state highway agency. So we have here a table showing to us the gradation requirements for aggregates in Portland cement concrete. ASTM designation C33. So we have here a sheave designation and the corresponding percent passing by weight and aggregate designation. Then the next one is the water. Of course, this the main water requirement stipulated is the water used also should be suitable for drinking. So this requires the quantity of organic matter, oil, acid, and alkali should not be greater than the allowable amount in drinking water. So which means that the water that you're going to use for rigid pavement is the water that is suited for drinking. So the alkali, the acid, the organic matter, the oil, it should not be greater than the allowable amount that is required for drinking water. So we have here a table showing to us the AASHTO recommended particle size distribution for fine aggregates used in Portland cement. So you have the sheave number and you have the mass percent passing. So this was adopted from a standard specification for transportation materials and method of sampling and testing. So from the AASHTO. Then we have the next one, the reinforcing steel. So steel reinforcing may be used in concrete pavement to reduce. Actually, the main objective for using a steel reinforcement is to reduce the amount of cracking that occurs as a load transfer mechanism at joints or as a mean of tying two slabs together. So steel reinforcement used to control cracking is usually referred to as temperature steel, whereas steel rods used as load transfer mechanism known as dowel bars, and those used to connect two slabs together known as tie bars. So for the reinforcing steel, we have what we call the temperature steel, provided in the form of a bar mat or wire mesh consisting of longitudinal and transverse steel wires welded at regular interval. So we have also a reinforcing steel bar. We have the dowel bars, which is used mainly as a load transfer mechanism across the joints. They provide flexural, shearing, and bearing resistance. And you have the last one, which is a reinforcing steel bar also, which is a tie bar. This tie bar are used to tie two sections of the pavement together, and therefore they should be either deformed bars or should contain hooks to facilitate the bonding of the two sections of the concrete pavement with the bar. So these bars are usually much smaller in diameter than the dowel bars and are spaced at larger centers. Typical diameter and spacing of these bars are 3/4 inches and 3 feet respectively. Then we have joints in concrete pavement. So actually there are different types of joints that is being placed on a concrete pavement. So the main objective is to limit the stresses induced by temperature changes and to facilitate proper bonding of two adjacent sections of pavement when there is a time lapse between their construction. So for example, between the end of one day's work and at the beginning of the next. So actually these joints can be divided into 4 basic categories. So we have here, you have the expansion joint. So the expansion joint, actually, when concrete is subjected to an increase in temperature, it will expand, so resulting in an increase in length of the slab. So basically, when the temperature is sufficiently high, the slab may buckle or blow up, which is sufficiently long, and if no provision is made to accommodate the increased length. So therefore, there is a need for an expansion joint that should be placed transversely at the regular intervals to provide space for the slab to expand. So this is the illustration how the expansion joint is being installed. Then we have the contraction joint. Contraction joints actually is subject, we have to take note that a concrete pavement is subjected to the decrease. If it is subjected to decrease in pavement, the slab will contract if it is free to move. So prevention of this contraction movement will induce tensile stresses in the concrete pavement. So it is basically the main reason why we have to place a contraction joints. It is placed transversely at regular intervals across the width of the pavement to release some of the tensile stress that are induced. So basically, for contraction joint, it is basically used. It is being placed because the concrete is subjected to a decrease in temperature, and the pavement will subject to contraction, so that this contraction movement will be prevented. It is the main reason why we have to install contraction joints. Then we have the hinge joints. So we have here the hinge joints, which are mainly reduced cracking along the central line of highway pavement. So this is a typical illustration for a hinge joint suited for a single lane at a time construction. Then the last one is the butt joint. So we have here an illustration for the installation for a butt joint as one of the joint that is being constructed on a rigid pavement. Types of pavement highways. So basically, for a pavement, for a rigid pavement, it is divided into three groups. We have the plain concrete pavement, the simply reinforced concrete pavement, and continuously reinforced concrete pavement. So this jointed plain concrete pavement is known also as JPCP. It has no temperature steel or dowel for load transfer. However, as steel tie bars are often used to provide a hinge effect at a longitudinal joints and to prevent the opening of these joints. So for plain concrete pavement, these are used mainly on low volume highways or when cement stabilized soil are used as sub-base. Then for our simply reinforced concrete pavement, they have dowel for the load transfer of traffic load across joints, with these joints spaced at larger distances, which ranges from 30 to 100 feet. So temperature steel is used throughout the slab, with the amount dependent on the length of the slab. So tie bars also are used commonly at longitudinal joints. Then the third one is the continuously reinforced concrete pavement, or CRCP. So continuously reinforced concrete pavement have no transverse joints except construction joints or expansion joints when they are necessary to specific positions, such as bridges. So these pavements have a relatively high percentage of steel, with the minimum usually at 0.6% of the cross section of the slab. They also contain tie bars across the longitudinal joints. Now we move on to pumping of rigid pavement. So you have to take note that pumping is an important phenomenon that is associated with rigid pavement. So basically, when you talk about pumping, that is the discharge of water and subgrade or subbase material through the joints, the cracks, and along the pavement design. So it is actually caused by repeated deflection of the pavement slab in the presence of accumulated water beneath it. So what is the manifestation of pumping? So that includes discharge of water from cracks and joints, spalling near the center line of the pavement, and a transverse crack or joints, mud boys at the edge of the pavement. We have the pavement surface discoloration, breaking of pavement at the core. So what is the major design consideration in order for us to prevent pumping? So basically, it is to prevent pumping, you have to reduce or eliminate the expansion joints, since pumping is associated with these joints. So it's the main reason why the present design or the current practices limit the number of expansion joints to a minimum.